If Akshay is here, please join back. Or please ask him to join back. Okay. So, are you all able to hear me? I hope I didn't get
Yes, ma'am.
disconnected. Yes, ma'am. Okay, okay, okay. All right. So we wrote down the variable elimination algorithm yesterday. So today, what I want to do is I just want to demonstrate this with some examples, which slightly larger examples. So the form is this. The input is a query and some evidence. You're given this, and this is what we want to evaluate: the probability of a query given E1 to EK. So in this case, this is like you want to get the whole table, the probability tables of Q given E1 to EK. So E1 to EK, sometimes, if you have it in this form, it is that, for all possible values of E1 to EK, you want to get the probability of all possible values of Q. Okay, so that's what this means. If you wanted a particular instantiation, maybe you would write something like this: probability of Q given E1 equal to E1 and EK equal to EK. So okay, so this some notational things. So something like this. Okay, so this is how you would write it. So this means for a particular value of evidence, you want this conditional probability. Okay. And in general, there are some other hidden random variables. So what you do is you need to do a join over these hidden random variables, because ultimately you want the joint over all these random variables together, all the random variables in the network. So you keep picking each hidden variable, do a join over that hidden variable, and then finally eliminate it, and keep cycling over this whole set. Not cycling, keep visiting each element of this hidden variable set. And finally, when you're done, you do a join or normalize, depending on what the query is. So let's just see this, so that it makes more sense. So here I'm just again doing a slightly larger network. Not this is also not too large anyway. So this is the same network that we have been using. So this is the burglary random variable. It's all these are Bernoulli. So that's burglary, earthquake, and this is a random variable which says the alarm fires or alarm doesn't fire. Okay, and then there are two variables which say that John calls and Mary calls. These are your neighbors. So a query that you might want to find is what is the probability of burglary happening or not happening given John called and Mary called. Okay. So these are very specific values. This means J equal to J and M equal to M. Okay, so generally J can be 1 or 0, M can be 1 or 0. So if you put 1, 1, it means that what's the probability of a burglary happening or not happening given John called and Mary called. So these are the kind of things you want to find. So suppose this is the query. Okay. So now what are the hidden variables here?
A and E.
A and E, right? So the hidden random variables are everything that doesn't show up in the query. So that is A and E, right? So to evaluate this query, what you need to do is you need to do some intermediate operations as given by the algorithm. So let's say, so basically you need to do some joins, right? So the initial factors, so let's just write down what are the initial factors. So can somebody tell me what the initial factors to consider would be? So this is a particular value of J and M, and B, you're interested in all possible values of B. So probability B equal to any B. So probability B equal to B given J and M for all values of B. That's what you want. Okay, so what would the initial factors be?
P of B, P of E,
P of B, P of E,
P of A given B,
P of A given BE,
P
yes.
of small j given A, and
P
P
of
of
small
small m.
j, yeah, exactly. And P of small m given A, right? So these are the initial factors you consider. So the small g and small m, you only consider that. I mean, this table would have for all entries of j and a. But what you only do is you just pluck out the part which has j, small g. Okay. And similarly, the same thing for m given a. Now, suppose I say I'm going to do a join over a. So I'm going to do a join over A. So what this means is like join all factors which have A. Okay, so it's not necessarily that only two factors. You can do a join of multiple factors. So what are the factors to be joined here?
A given B, comma E, J given A, M given A.
Yeah, so these three, right? So join of these three quantities and these three factors. So what will it give you? What's the result of a join operation?
P of JMA given BE.
P of J M A given B E. Right? So basically, A comes up in both sides of this bar. So it's a condition variable as well as it's an unconditional variable. So what you do is you just put it on the left hand side. Okay, and B and D always come on this side of the bar, so you always have it as this part. And JM always come on one side only, so that also comes here. And this is a probability. This new factor that you get is a probability because you've done a join of all the factors which have A. Okay, so if you did just a join of two things, I mean, if you went step by step, then you have to just be careful, like whether it's actually a probability or not. So this we saw some examples yesterday. So anyway, when you join all the factors which have A, you're going to get a probability table. So now the new factors that you are going to get are, so this is one, and so you can completely ignore the others which you joined together. You can just have these, and you can have P of B and P of E. Okay, so this is the new factor. So you can, if you're trying to implement something from scratch, what you can do is you can just completely erase these tables out from memory. So that's what it is. And now you have these new factors. And what can you do now? So as per the algorithm, you're trying to, remember the objective is to keep the table size as small as possible. So that's why you do a join and immediately you can do an eliminate. Because the hidden variable, once you eliminate it, it's as if you have the network size itself is a smaller one. Okay, so that's why you can just eliminate it. So the tables also become smaller. So what would that mean here? What do you need to eliminate now?
Join over, eliminate over A.
Eliminate A, right? So eliminate A. So that will give you what? So P of B and P of E remain. So eliminate A from this table. So what do you get?
P of J, comma M given B, comma E.
P of JM given BE. Okay, fine. So this you got. So now what is the next operation to be done? So
Second
this,
hidden variable,
yeah, second hidden variable. So which is
P of E. E.
E. Yeah. So now you're done with A. So this is done. So now you have to take E. Okay. So this is as if you're saying that now you only have BE. So it's as if the network changes. You only have BE and JM. A has been like removed out. Okay. All right. So now what does a join give? So join over E is what you do next. What do you get? So which are the tables?
Second and third.
So these two, right? So you join these two and you get what?
P of
Yes.
J M E given B.
Yes, P of J and E given B. And there is also P of B. Okay, so these are the new factors. And now what do you do?
Eliminate E.
Eliminate E. Eliminate E. So you're left with P of B and what should I write here?
P of J M given B.
P of JM given B. Okay, so you've done all these operations now. So you have eliminated both A and D. You've got, I mean, you got rid of the hidden variables, and so basically this part is complete now. And what you need to do is do some join or normalize. Your query was this P of B given JM, and what you have is P of B, P of JM given B. So what you want is P of B given JM. right? So what do you do now? How can you get this using the operations that we discussed?
Join over B and then normalize over J and M.
Yeah, so join over B, join over B. So that gives you P of, what do you get?
JMB.
JMB. Okay. And now what you do is you can just do, since you wanted this quantity, so this table would have JM and maybe like plus B some value, JM minus B some value. So if you sum up all these entries, you're going to get P of JM. Okay. And so what you do is a normalize operation. So if you do a normalize, so you normalize this table. So that will give you P of B given JM. Right? So what it means is you take this entry and divide it by the sum. So maybe like 0.2 and 0.7, if that was what you had. So the new table, this is going to have J, N, and what are the values that will be there? There'll be plus B and minus B, and what are the numbers that would that this normalized operation would give you?
2 by 9, 7 by 9.
2 by 9 and 7 by 9. Okay, so that is the final result. So this is the output of the variable elimination algorithm. Okay, so at each point you have to do these computations, and finally you get the desired value. So this table is what is going to be the output of the algorithm. So it's basically that's what you wanted. The query you had was, what's the probability of B equal to some B given some particular values of J and N. And you wanted this probability for all values of B. Okay, so this is one thing we did. And if you notice, there's some ordering that we followed here. So we first did, we did join over. So the order we followed here was, A and E, right? So we did a join over A and then we did an eliminate, join over E and then eliminate. Okay. Now you could have also done a join over E and a join over A. Okay, you could have an alternate ordering was to do E and then followed by A. Okay, so in that case you would get, your intermediate factors would be different, but finally you would get the same table. The result would be the same. So what I would say is, try this out also. So as a homework, try out the ordering E and A. So homework is to try the ordering E, A.
Ma'am,
Yes.
could you once explain the normalized part again?
Yeah, sure. So yeah, you get up to this part, all the join and eliminate steps.
Yes.
Yeah. Right. So at this point that you had, after you followed whatever was given in the algorithm, the join and eliminate steps, what you got was these two tables. You were left with these factors, P of B and P of J and given B. Now go back to your query. What you wanted was a P of B given Jn. That's what your ultimate result had to be. So you wanted some way to get P of B given Jn from these factors. So essentially what you're using here is just this definition of this conditional probability. So P of B given Jm, it's just P of B, J and M divided by probability of Jn, right? And this probability, okay, so the numerator, you can just write it as such. Now the denominator is just sum over all possible values of B, P of J and B. Okay, so essentially what you needed was this P of J and B. You needed a new factor which had this P of J and B. So that's the reason we did this join. Okay, so since we wanted these kind of joins, so we know that if you do a join of tables, what you get is that's what can give you, a joint distribution. Okay, so that's what we did here. So P of B and JM given B. Now that is going to give you this probability JMB. It's just by the multiplication rule, the chain rule. And so now from JMB, you wanted again B given JN. So what normalized does is, if this is the table, so P of J and B, if this is this table, these entries here are P of J and B. It's the full joint over J, M, and B. Okay, and so if you sum up these tables, this has just two entries because B can take just two values. Now, if you sum up these entries, you're going to get this probability, the denominator. Okay, so the sum of these two entries is 0.9. Okay, so this is 0.9. Okay, that's the sum of this. Now, in order to get this P of B given Jn, the normalized operation, what it just does is it takes this table and then it divides each of these terms, this 0.2 by the sum, 0.7 by the sum. So that will give you 2 by 9. So 0.2 by 0.9. So you get 2 by 9 and 7 by 9. Okay, so that's what the normalized operation does. It's just each element you take, each row or each entry, each number in the table you take and divide it by the sum of all the entries. So that's what is the normalized operation. Okay, so you have to see now once you reach this point, depending on what your query is, you have to see what operations are needed. So suppose you just wanted P of J and B. So if that was all you wanted, then you didn't need a normalized step. Okay. So this part is, you have to decide what exactly is the operation to be done depending on the query you evaluate. Okay. So Kushbu, is it clear?
Yes, ma'am.
It's clear. Okay. So yeah, as I suggest that all of you try this out with this ordering, like where you join over E and then you join over A, and finally you will get a table in the end. So something, some set of factors you get, and from that you try to again compute B given J. So you will, yeah. So just try this out. Okay. So here, like one more point I just wanted to illustrate here is, just try to see what are the number of factors, what are the number of entries in the factors that you get, right? So here, let's take the initial factors. How many entries are there in each of these tables? Can somebody tell me? So number of entries in the table or table size is how much? So you just tell me like number of probabilities which are there in the table. So can somebody tell me P of B, how many?
Two.
This is
2.
2. P of 2. Here,
8,
8.
2,
This one, 2.
Four.
This is also 2, right? Okay, so 2, 2, 8, 2, 2. Now, when you go to the next part, how many entries are there? This is the same, there's no change. What about here?
8,
This is 8. Okay, and so when you do an eliminate, what happens? How many entries will be there in this factor?
4,
4. And so this is 2, and now
4,
so this is also 4. And when you come to this part,
2 and
2.
2 and 2.
This is also 2, right? Okay, and yeah, going forward, everything has just 2 entries. So the maximum table size, so these are the table sizes, and this is what actually decides the complexity of variable elimination. So there is also this order which is tied to it. Okay, so now what I want you to see is, if you do it with E and A, when you do this analysis, when you do this variable elimination, also try to see the size of the factors. Is there any difference? Okay, so that's something that you should also do. We will now just do one example where I know for sure that there is a difference in the factor size, where the difference is quite huge. So I just want to illustrate that one to you. So let me just give this new example. So this is example 2. So this is something like this. You have one random variable like this, and there are a couple of random variables like of this form, x1 to xn. So maybe n can be something like 100, okay? And you have something like this, y1 up to yn. Okay, so this is basically a tree structure that you have. So x1, x2, and similarly x3 also, like you have this. And here you have y2 and y3 like this. So this is the structure of the network. Okay, and let's just take the case where all of them are binary valued again. And now what I'm saying is I want to evaluate this query. So I'm seeing y1s, all these y's I'm going to see. And I want to see what's the probability of xn given y1, y2 up to yn. Okay, so this is the query I want to compute. Okay, so let's try to do variable elimination here. So this is the query. And what are the hidden random variables here?
Z and x1 to xn minus 1.
Z, x1 and xn minus 1. And the initial factors are you have p of z. So let me just write it down. So the initial factors that you start off with is p of z. Can you tell me what are the other factors?
P of x1 given
X1.
z, similar to
X1.
p x z and xn
Yeah,
given
so
z.
all the way, right? P of x n given z. Yes,
P
then
of y1 given x1 all the way till p of yn given xn.
P of yn given xn. Okay, yeah. Okay, so these are the factors that I have, and the hidden variables are z, x1 to xn minus 1. Okay, so now let's fix this ordering itself. I'm going to start with z, then I'm going to take x1 and up to xn minus 1 for my variable elimination. So first thing I'm going to do is a join over z. So what do I need to do? What are the factors that I have to join?
P of z and p of xi given z.
Yeah, so basically all of these, right? Wherever z comes, you need to join all of them. So what's the new factor that you get here? So maybe let me ask somebody else. Like Kushbu, maybe you want to tell me what you get here?
Ma'am, it would be the joint probability of all
Yeah, so basically of all
x, overall x.
and anything else is conditioned or anything.
And z.
And z also, right? This is the probability you get. Okay, and so now I'm going to eliminate z. Right, so what do I get?
P of x1 till xn.
P of x1 till xn. So my new factors are now p of x1 to xn, and basically all these p of y1 given x1 and p of yn given xn. Okay, so what do I need to do now? What's the next step?
Join over x1 and eliminate x1 and do for all x.
Yeah, okay. So let's just do one of them. So join over x1. So what do you get if you do a join over x1? So basically these two you need to join. So what's the result?
P of x1 till xn comma y1.
P of x1 to xn and y1.
Y1.
Yeah, and the remaining factors remain the same. P of
Remain the
y2 given x2 and yn given xn. Okay. Yeah, and then what do? You eliminate x1. Okay, so you eliminate x1 and that will give you p of x2 to xn y1. Okay, and you keep doing this and these factors remain as such. And the next step would be join over x2 like that. You keep doing this, right? And finally, what would you get after? So you need to go till from z x1 up to xn minus 1. Right, so let's just write the last step. So what would you start off with at that point? Like you're at this stage, you've joined and eliminated x1 up to xn minus 2. Okay, so what is the factor that you will get here?
P of
P of
xn
x
and
comma yn.
yi up to yn minus 1.
So you'll get p of x. Can you say that again? I just didn't catch it.
xn joined with y1 up to y of n minus 1.
Yeah, y1 up to yn. So y1 up to yn, right? Or-
N minus
n minus 1.
Okay, up to n minus 1. And what else?
P of
P of y1 by x.
Yn given xn. Okay, so now, okay, so this is you have eliminated all the hidden quantities, right? And what do you do next? Are we
Join over
done
X.
here? Yeah, we need xn. Okay, so next step is to join over xn. Right, so what does that give you?
P of Xn and y1 up to yn.
Yn up to yn. And then what do you do?
Normalize over
Normalize.
y1 to yn.
So normalize over basically all these values over y1 to yn. So that will give you xn by y1 to y, xn given by y1 to y. Okay, so here, like now, if you just try to analyze the size of the tables, right? So what happens here? How large is this table? Okay, let's start with the initial factors. Let's take all of them a binary. So how large is this?
2,
2. This one, each of these?
4,
4, right? All of these are 4. Okay, so all of these are 4. What happens when you do a join over z?
2 to the power n plus 1.
Yeah, this becomes a large table, right? 2 to the power n plus 1. And so what happens in the next step when you eliminate, what if we eliminate z here? So how big is this?
2 to the power n plus 1.
So this is again 2 to the power n, right? This table, and then here all these are still 4. And it kind of like it drops down after that. So maybe like at this point, or no, you still have 2 to the power n, right? So n minus 1 and 1 variable here. So yeah, so you get 2 to the power n at every point. Okay, so this is like this kind of ordering. I mean, you still haven't overcome there's some inherent hardness here. Like it's still an expensive operation that's being done here if you go with this ordering. Okay, so now what I just want to do is just take one other ordering. So
Excuse me,
maybe
ma'am.
yes,
Ma'am,
please.
yes, ma'am, in the slide, yes, ma'am, where you wrote that elimination of z, where p of x1 to p of xn. Here you wrote the total number of factors is 2 to the power n only. No.
Which one? This one?
Ma'am, below join over x1.
Okay, this
Here,
one.
ma'am, we start from the x1 and we reach up to the y1. So the factor is 2 to the power n plus 1, I think.
Oh, okay, right. So this has to be in plus 1. Right. So I think this one, I think I was writing about this one, x2 to xn and
Okay.
y1. So that is 2 power n.
2 power, yes.
Yeah, but generally, yeah, I mean, this, thanks, Rishabh, for asking this. So generally, you see that there is this huge exponential number, 2 power n kind of a dependence that's there, where the number of random variables is also order of n. So the number of random variables here is 2n plus 1. Okay, so this is order of n. And what you have here is an exponential number, right? So this is not a very nice thing that happens with this ordering. But now let's just try a different ordering. So maybe let's take x1 to xn minus 1 and z. Okay. So this is option 2 maybe. Option 2 is to take x1 to xn minus 1 and z. Okay, if you fix this as the order of join and eliminate operations, right? So let me just take this as such. Just copy this down. Okay, so this is the order I'm fixing. So what happens now? Can you tell me these are the initial factors. Okay, and I'm starting with x1 to xn minus 1. And then z. So what happens? The first join operation will have what all?
P of x1 given z and p of y1 given x1.
So you join p of x1 given z and p of y1 given x1. So what's the new factor you get?
x1 comma y1 given z.
x1 comma y1 given z. Okay, and now you do an eliminate of x1. Okay, and what do you get?
P of y1 given z.
P of y1 given z, and all other factors remain. So basically you can do away with, you can't do away with this one. You can do away with these two. And what you have is x2 given z up to xn given z. Okay, and you also have y2 given x2 and p of yn given xn, and you are also going to have p of z. Okay, so yeah, so here you see that the size of these factors is going to be much smaller. Okay, so let's just do one more step. Maybe the next one is to take x2, right? So this is the operation, this is the order that we fixed, x1 to xn minus 1 and z. So now if you do a join over x2, okay, so what is the new factor you get? Which are the tables that you merge?
P of x2 given z and p of y2 given.
Yeah, basically these two, right? And what do you get?
P of x2 y2 given z.
P of x2 y2 given z, and all others remain the same. And finally, you're going to do an eliminate of x2. Eliminate x2, so that will give you P of y2 given z, right? And so you see that, again, the size of this table is not going to increase. The max, I mean, you can do this for every n. And so what you get is the maximum size here is just this one, right? 2 power 3 here. So this is 8. Okay. And so this is the join step is typically the most expensive operation, and eliminate is going to bring the size down. Okay, so even the largest one is 8, and that's not it's not very expensive that way, as opposed to here, like the previous option, the order that you had here was like 2 power n. Okay, so that's a very large table, right? So with some intelligent reordering of the random variables, sometimes you can get a very efficient way to compute these kind of queries. So what I would say is, you try to do this, complete this. In the end also, whatever you're going to get is, this is going to be like the maximum size, right? So the takeaway here is that, for different kind of orderings of random variables, you're going to get different complexities. Okay, so what is the number of orderings that you can have? So if there are h hidden variables, what's the number of orderings possible?
H factorial.
H factorial.
H factorial, right? So basically a permutation of all these h variables. So to search for, you can actually, try to search for the best ordering, okay, beforehand. So what this means is that, you don't actually go and compute all these values. Beforehand, you try to, go through these h factorial orderings and try to see the best. Okay, and so this is something that you can do. You don't have to compute the tables. Now, once you've found the ordering, you actually go ahead and compute the tables as such also. Okay, so this is the general thing. Now, h factorial also, like if you have like a large number of hidden variables, this is also a big number. H factorial is going to be a large number. Like if you have 100 hidden variables or something like 100 factorial, so that may not be possible to find the best over there, like by going through each of them. So what you do is typically you use some kind of heuristics. So beforehand, like you start off with this query and you have all these hidden variables. Now, one possibility is to choose a hidden variable, which leads to the smallest increase in the size. Okay, so you look at all of these, and at this point, just do one step and see how big it's going to be. And so it's like a greedy choice. Okay, so that is something that people do often. Instead of trying to write out all the orderings. So now, so as per this, so we saw this, right? We did one evaluation with z. If you choose z as the first, what is the new table that you're going to get? You had 2 power n plus 1. Whereas if you chose x1, the maximum size of the table is just going to be 8 for a join. So it's the same thing for all x2 to xn minus 1. If you chose any of them as well, you're going to get this 2 power 3 because there's some symmetry in the graph. So it doesn't matter whether you choose x1 or x2. So that you're kind of indifferent to those. So what you can do is, you just compute one step and see which one is going to be the, which is going to give you the biggest table size, or rather the smallest table size. The smallest table size is given by x1. So then you can say, okay, we will do this operation. Now go ahead, do this operation. And after this, at this point, again, you come and see like which y's, I think it was y's, right? Or no, y's were observed. So x2 to xn or z. So which of them would be beneficial to join? Okay, which of them would give the smallest size? And you keep doing this till the end. Okay, so this is like a greedy choice. So you can make a greedy choice of which element, which random variable to join. Okay. So this is one thing that people do. And so one thing I also want to mention here is there can be some graphs for which, if you take all possible orderings, all these H factorial orderings, there can be some graphs and some queries for which if you take all possible orderings also, you might not get this kind of thing that happened here. For this graph, there was this ordering which gave you an efficient way to compute, which gave small table sizes, but that may not happen always. Like for every ordering, it might happen that the table sizes, the maximum table size that you get is always large. Okay, so in that sense, this problem, this inference problem is actually NP hard itself. Okay, so I'll just show you, I won't do the hardness proof, but what happens is there is this reduction from the satisfiability problem, which we know is hard. So what it means is that, you can solve the satisfiability problem. Any instance of the satisfiability problem can be solved by, mapping it to a Bayesian network. You can construct a Bayesian network, and if you solve the, a particular query on the BaseNet created, that will solve the satisfiability problem. And since the BaseNet, since this query, this inference problem solves the satisfiability problem, it has to be that it cannot be efficiently doable, because satisfiability is hard. So if there are hard instances, now it means that that particular BaseNet is a hard, that particular query on the BaseNet is hard. So I'll just show you that particular graph. So this is from the book of Daphne Koller and Friedman. So they have this big fat book on probabilistic graphical models. Okay, so this is taken from there. So this is the kind of network. It's not a very hard network in that sense. Then there are not like too many connections, but it turns out that for this BaseNet, if you want to find the probability of X, okay, so this network is constructed in a very special way. From the satisfiability problem, there are some clauses that you have in satisfiability, some Boolean variables, and you want to see if there's a way to satisfy all these clauses, right? Just to remind you of the satisfiability problem. So this is a way in which they've given a representation in terms of a BaseNet, and here if you try to find probability of X, okay, if your query is just probability of X, there it turns out that if you try to compute all possible orderings, you'll always get an exponential size of the tables. Okay, so I'm not going into more details here. So this is just to illustrate to you that variable elimination, this algorithm is not efficient always. Okay, so there is a hardness here, but for some special graph structures, it works. You can have, this is efficient. You can find some efficient orderings. So one example, where variable elimination is efficient is in what is called these polytrees. So variable elimination, so it's NP hard in general. Okay, this the problem itself is NP hard. So that's what I mean when I say that this is the variable elimination is hard. What I mean is the problem, the underlying inference problem is NP hard in general. But when you have special cases like trees, okay, or I'll call it polytrees, is that because that's the usual jargon used. So polytrees, so these are just trees, the regular tree graphs. Okay, but additionally, you don't have any cycles. You don't have any undirected cycles. Okay, so maybe something like this, right? Yeah. So this is not a polytree because there is, if you take it as an undirected graph, there's a cycle. Okay, but something like this, yeah. So all our usual notion of trees, that that this is a poly tree. Okay, and yeah. All right, so for these kind of graphs, okay, so basically trees, okay, for all practical purposes, those are trees. And for trees, you know, it turns out that variable elimination is efficient. So there is an efficient ordering that you can come up with, so that variable elimination, this algorithm, gives a very nice way to compute. Okay, so you can try to think what happens, like what is the ordering that you need to come up with for these kind of trees, for these tree graphs. What is the ordering that works? This is something that, you know, I leave it to you to think about it. So this brings me to another point about, you know, these tree graphs. Okay, so this is an example where, you know, for these network sizes, of these network problems, generally there are hard problems, but for some special cases, you have efficient ways to do things. So trees, you know, in many contexts, so this is, you saw one example here, so this is in graphical models where you want to find some probability. For tree graphs, you know, the computation is efficient, it's known to be efficient. This is something to, you know, carry with you or take away with you, because, you know, from my experience, I've seen that, you know, in a lot of other problems which are actually not related to, you know, these kind of AI or graphical models, not, it needn't be really related. We generally find that, you know, there's something about these trees. Okay, it's probably about the connections, the lack of connections, and a very specific way in which the nodes are connected. So for, you know, several problems out there, we see that with tree graphs, things become much easier. Okay, so this is something to, you know, I just thought it's something that you might like to, you know, note, or, you know, just as a takeaway. Okay, so all right, so are there any questions so far? I know I skipped some of the details. I would have liked to show you the NP hardness proof, but I think we have to move to some other topics, so that's why I'm not
Ma'am,
doing it. Yes, Advait.
is it necessary that the random variables that we have here, that they should be discrete?
Yeah, not at all. So we have talked of discrete random variables for all these problems that we considered. So there are extensions of these ideas to the case of continuous random variables as well. So what changes is that instead of these summations, what you're going to have is integrals. Okay, so generally, you know, the inference problem is not really easy for even continuous random variables. When you have this integral, evaluating an integral, that is something that you never know. The form of, so what you'll have here is some density functions. So these probabilities will be, instead of this probability mass, so here we have the probability mass function, there you're going to have densities and some integrals. So there, you know, the problem is slightly harder in some sense, because the particular join operations that you do, if the densities have a very particular form, only then can the integrals be computed efficiently. Okay, so in that sense, it's a slightly harder problem when you go to the continuous space. But yeah, these ideas extend there too. The analysis, the way in which you try to do an analysis or try to compute a query, the similar techniques, you can use it to analyze, but some of these, there's some more hardness aspects that come up there. Okay, so in that sense, yeah, these are, we just do the discrete case here for this course, because some things are, a little bit easier to visualize for discrete. But yeah, generally, it also holds to continuous random variables. Okay. In fact, this book that I was showing you, they had these, they have, if you're able to see this screen, so they have like these 4 parts, right? So this first part is entirely about the BaseNet representation. And here they have these kind of Gaussian network models as well, right? So this is like continuous distributions. And what do you do there? What does it mean? What does a BaseNet mean there? So there are some things in that, and generally this is a broader class which is called the exponential family. Okay, so it generalizes Gaussian distributions in some sense. Okay, so so I just felt like, you can refer to this for more details. There are a lot of references for continuous case too. Okay, this book might be a little, they try to cover every aspect possible in base nets. So in that sense, it's nice. Like whatever you want to find, if there has been some body of work there, you will find it in this book. But yeah, maybe I would suggest it as something that when you're bored, when you want to try some new things, you can go through this. Okay, but this is not going to be there for your exam as such. These kind of minute details, I'm not going to question you on that. Okay? But yeah, you should know that you can do this for continuous random variables also. That's an important point. Okay. Any other questions? Okay, so I think okay. So what I'll do is, okay, we are running out of time, so we'll have a class tomorrow. So there, what I'm going to do is I will, my initial plan was, since there is this hardness, right, for inference, I was thinking of doing sampling, which is a way which people use to overcome this hardness aspects. But since in your lab you have one last part on these decision diagrams, so what I'll do is it's an allied concept to BaseNet. So tomorrow what I'll do is I'll talk a bit about decision diagrams, and after that we'll do sampling. Okay. So all right. So thanks everyone for being here. I'll just hand back if there are questions. So if not, see you tomorrow.